Hello and welcome to Physics Talk. Here we discuss various topics on physics and try to clear all your doubts. So come on, let's begin. The topic we are going to discuss today is how nucleons are distributed inside a nucleus. So first let us understand what is meant by the distribution. We know there are two types of particles inside a nucleus, namely proton and neutron. The term nucleon is used to refer to both these particles. The question that naturally arises is how these nucleons are arranged inside a nucleus. It could be that all the particles are uniformly distributed inside a nucleus, or maybe that the nucleons are mostly present in the interior and their density gets progressively decreased towards the surface regions. Or it could be the reverse case also, where nucleons are mostly present at the periphery while the interiors are largely empty. These are just three examples of how the distribution could be. There are many such arrangements that we can imagine. The question is, how is the actual arrangement of the nucleons inside the atomic nuclei, and that is what we are going to discuss. The simplest way to study the nuclei is to strike them with some probes and observe the deflection produced in the outgoing particles by the nuclei. In other words, performing the scattering experiments with nuclei as the target and subatomic particles or photons as the projectiles. So let us first find out what type of particles are suitable to be used as projectiles. There is a criteria for choosing the projectile, and that is the wavelength of the probing particles must be of the order of the size of the nuclei under study or smaller. Obviously, visible light doesn't fit the bill, as its wavelength is many order of magnitude greater than the nuclear size. On the other hand, gamma rays, which has much shorter wavelength, could have been suitable from this perspective, but it has some other disadvantage. Nuclei inside atom are surrounded by electron clouds, and electromagnetic waves interact more strongly with these electrons rather than the nuclei inside. Hence, employing particles rather than electromagnetic waves or photons would be a better option. The subatomic particles, proton, electron, and neutron, have been employed for this purpose. If we compare the suitability of these particles, protons and neutrons have the advantage that at comparatively lower energy of about 20 MeV, their wavelength becomes sufficiently short as per requirement. On the other hand, for electrons, in order to have requisite wavelength, they have to be accelerated to over 100 MeV energy, which is more difficult to achieve. Even then, electrons have one great advantage over protons and neutrons as probing particles. That is, electrons interact with nucleus through electromagnetic interaction, which is very well known, whereas neutron interacts with nucleus through nuclear interaction, which is more complicated, and proton interacts with nucleus through both nuclear and electromagnetic interactions, making it even more complicated. Thus, electrons are most suitable as probes. The experimental setup is like any other scattering experiment. There is an electron source, a thin foil of target material, and a detector. Electron beam from the source is first accelerated to suitable energy, and then the beam is made to strike the target material. The scattered electrons are detected at various angles with respect to the incident beam direction. The experiment is performed with different types of target materials, and the intensity of scattered electrons at various scattering angles are measured for all of them. The plot of the results looks somewhat as shown in the figure. It can be observed that the intensity of the scattered electrons going down for higher scattering angles as expected for all the representative nuclei. And heavier the nuclei, overall intensities at all angles are higher than the lighter nuclei. These results can be simulated theoretically by assuming a nucleon distribution inside the nucleus. The procedure starts with first assumption of a density distribution of proton and assuming that the neutron also have the same density distribution. Then the probability of deflection of the electrons by this density of proton is calculated theoretically. The aim is to match the probability of electron scattering at various scattering angles with the experimentally determined intensity of electrons at those scattering angles, because the intensity of electrons at one specific scattering angle should be proportional to the probability of scattering of electrons at that angle. So first assumption is made and the calculation is done. If this calculation does not match with the experimentally determined electron intensity, then another form of density distribution is found. In that way, the process continues until one density distribution is found that correctly predicts the intensity distribution of electrons at various scattering angles. The proton distribution or charge distribution inside nuclei that can lead to the observed results of the scattering experiments is given by this expression, where rho is the nucleon density that is varying with r, which is the distance from the nuclear center taken as the origin. The other terms I shall explain from the plot. When the plot is drawn for the nucleon density rho against the distance from the center of the nucleus r, it looks like this. It can be observed that the density is uniform at the interior of the nucleus and then it drops down, initially at slow rate, and then there is a steep fall up to the periphery region. This uniform maximum density at the interior is termed as rho 0. The distance from the center to a point where the nucleon density falls to half of its maximum value, that is half of rho 0, is called nuclear radius, represented by capital R in the expression. The small a in the expression is the measure of the surface thickness of the nucleus. It is taken such a way that the distance over which the nucleon density falls from 90% of rho 0 to 10% of rho 0 is equal to 4.4 times of A. Now let us look at a representative figure of one quadrant of a nucleus and the nucleons inside it. It can be seen that the intensity rho 0 is uniform at the interior and then falls down. The distance where it drops to 50% of the maximum value, shown with the thick black arc, is taken as the nuclear radius r. The region between two dotted arcs are the surface region whose thickness is 4.4 times of A. The density distribution can be visualized for a whole nucleus like this. However, I would like to clarify here that the fall in density is sharp and continuous, and there are no clear cut boundaries in between. The boundaries appearing here are because of the limitations of animation. After explaining all the terms in the density distribution formula, let us now discuss some important conclusions that can be drawn from the results of this scattering experiment. It is found that the results for all the nuclei can be arrived at by taking the value of rho 0 is equal to 1.65 into 10 to the power 44 nucleons per meter cube. Since this maximum nucleon density is same for all the nuclei, it means that as we go from lighter elements to heavier elements, the size of the nuclei increases progressively, maintaining the same density. That means the volume of the nuclei must be proportional to their mass numbers. If we roughly assume nuclei to be spherical in shape, then their volumes are proportional to the third power of their radii. Hence, nuclear radius is proportional to a to the power one third, where a is the mass number. The value of the proportionality constant found from the experiment is 1.07, and thus R is equal to 1.07 a to the power one third Fermi. The second important conclusion is regarding the value of the parameter A, which is related to surface thickness. It was found out to be equal to 0.55 Fermi for all the nuclei. This is a very important and significant finding. The meaning of this result is that the nuclei, no matter how big or small, the thickness of their surface remains the same. In this way, from the scattering experiment using electrons as the projectile, we have got a fair idea about how the nucleons are distributed inside the atomic nuclei.